At certain times, it feels as if the universe itself is sending us a hidden message. And the closing days of September 2025 became one of those rare intervals. 2 remote stars went supernova, unleashing torrents of high-energy radiation across our celestial neighborhood. Days later, Comet SWAN suddenly blazed to life, stretching its tail across degrees of sky. Moments later, the sun erupted violently, propelling a coronal mass ejection in the direction of the comet with timing so precise it defies statistical explanation. But this is just the prelude. Shrouded by the sun's overwhelming glare, the interstellar object, 3, divided by Atlas, makes its way toward Mars as October 21st approaches, creating a convergence of electromagnetic forces that could either confirm the most speculative theories in plasma physics or demonstrate the breathtaking power of cosmic coincidence. The next few weeks will reveal whether we're witnessing pattern or turmoil in the electromagnetic networks that bind our solar system together. Tonight, we journey into the unlikely convergences that are unfolding in the skies above us. And most importantly, don't miss what happens next. Because, as we'll see, the universe rarely offers such clear tests of its deepest mysteries. Part 1. When the sky exploded 3 times. September 26th, 2025. Universal Coordinated Time 0843. The cosmos delivered a 1-2-3 punch that should have astronomers questioning everything they thought they knew about coincidence. 2 stellar explosions had already torn through space. Nova V7994 Sagittari and Nova V935 Centauri, blasting the solar system with high-energy radiation just days before. Then, as if responding to some cosmic signal we can barely comprehend, Comet C, divided by 2025, R2-SWAN, suddenly erupted in brightness. Its magnitude jumped from a steady 6.5 to nearly 5.7 inches, a matter of hours, while its tail stretched across 2½ degrees of sky. That's 5 full moon diameters of shimmering ice and dust. But the universe wasn't finished with its symphony of destruction. 48 hours later, the sun itself exploded. September 28th, 0843. UTC, active region 4232 unleashed an M64 solar flare, the most powerful eruption our star had produced in 3 months. The timing eerily precise. The direction aimed directly toward the plane where SWAN was traveling through space. Now, any reasonable scientist will tell you this is coincidence. Random events clustering together because that's what random events do. The human brain, after all, is a pattern-seeking machine that can find conspiracy in a bowl of alphabet soup. But sometimes, just sometimes, patterns emerge that make even the most skeptical researchers pause and wonder if we're witnessing something far more complex than chance. Consider the players in this cosmic drama. SWAN had already passed perihelion on September 12th, surviving its closest encounter with the Sun and beginning its journey toward Earth. By October 20th and 21st, it will reach its closest approach to our planet, just 2,606 astronomical units away. That's roughly 10 million miles. Close enough to make this comet one of the brightest objects in our autumn sky. But SWAN isn't alone in this dance. Hiding behind the sun's glare, nearly invisible from Earth, lurks something far more mysterious. 3E Atlas, the 3rd confirmed interstellar visitor ever detected. This cosmic wanderer, discovered just this past July by the Atlas survey in Chile, is following a hyperbolic trajectory that will bring it to perihelion around October 30th, just inside Mars's orbit. The geometry is almost too perfect. Both objects traveling near the ecliptic plane, both embedded in the same turbulent layers of the heliospheric current sheet. That vast rippling boundary where the Sun's magnetic field changes polarity, both arriving at their most active phases within days of each other, just as solar cycle 25 shows signs of building towards something significant. And there's more. The new moon on October 21st creates the darkest possible skies for observers, coinciding almost exactly with SWAN's closest approach to Earth. It's as if the cosmos has arranged a front-row seat for whatever is about to unfold. Mainstream space agencies maintain their position. No proven causal links exist between stellar explosions, cometary outbursts, and solar activity. The United States Geological Survey continues to state emphatically that space weather shows no demonstrated connection to earthquake activity. These are the guardrails of accepted science, and we ignore them at our peril. Yet something in the timing feels orchestrated. Something in the sequence suggests we might be watching the opening movements of a cosmic symphony, where energy cascades from one system to another through pathways we're only beginning to understand. Could nova radiation somehow influence cometary volatiles? Could outgassing comets alter the local electromagnetic environment enough to trigger solar instabilities? Could the Sun's response create conditions that ripple outward to affect planetary systems? The questions multiply faster than answers. But here's what we know for certain. If this is choreography, rather than chaos, downbeat lands. Around October 21st, the new moon will darken our skies just as SWAN reaches its closest approach to Earth. Just as 3E Atlas skulks behind the Sun, approaching its own moment of maximum solar heating. Which way the coronal mass ejection pointed matters more than you might think. What counts as evidence for feedback loops between comets and our star requires careful definition. And what the period from October 19th through 26th might reveal depends on whether the tempo of cosmic violence increases or fades into the background hum of ordinary space weather. The stage is set. The players are in position. And somewhere in the mathematics of orbital mechanics and plasma physics, an answer waits to be discovered about whether we're witnessing the most elaborate coincidence in recent astronomical history, or the first clear evidence that our solar system operates as a more interconnected, electrically coupled machine than we ever dared imagine. The curtain rises on our cosmic mystery in just 24 days. Art 2. Comet SWAN's Sudden Awakening. September 26 began like any other day for comet observers. SWAN had been behaving predictably since its discovery, following the gentle brightness curve expected of a comet 2 weeks past perihelion. Then, in the span of just a few hours, everything changed. The first reports came from Southern Hemisphere observers around 0800 UTC. SWAN's coma had suddenly blazed to life, jumping from magnitude 6.5 to an estimated 5.7, bright enough to become visible to the naked eye under moderately dark skies. But brightness tells only half the story. The comet's tail, previously a modest smudge requiring binoculars to appreciate, had stretched into a magnificent streamer, spanning 2.5 degrees of sky. To put that in perspective, hold your hand at arm's length and spread your fingers. The distance from your thumb to your pinky covers roughly 20 degrees of sky. SWAN's tail now occupied more than an eighth of that span. A ghostly river of ionized gas and dust particles that would be easily visible to anyone with even modest optical equipment. This wasn't SWAN's first outburst, nor would it likely be the last. Comets are inherently unstable objects, particularly when they're loaded with volatile materials and subjected to the intense radiation environment of the inner solar system. As chunks of primordial ice and rock dating back 4 billion years, they carry within their nuclei the preserved chemistry of the early solar nebula. When solar heating penetrates deep enough to reach fresh reservoirs of carbon monoxide, carbon dioxide, or other hypervolatile materials, the resulting sublimation can trigger explosive outgassing events. SWAN's orbital position on September 26 placed it in a particularly interesting location, having passed perihelion on September 12th at approximately 1.2727 astronomical units from the Sun, closer than Mars, but not quite reaching Earth's orbit. The comet was still receiving substantial solar heating. More importantly, its trajectory kept it traveling close to the ecliptic plane, the imaginary disk where most planetary orbits lie, and where the Sun's magnetic field creates its most complex structures. This is where physics gets interesting. The ecliptic region is home to the heliospheric current sheet, that vast, rippling boundary layer where the Sun's magnetic field flips polarity. Imagine a ballerina's skirt spinning and undulating as it extends outward from the Sun at nearly 2 million miles per hour. This current sheet carries embedded magnetic discontinuities, shock fronts, and zones of enhanced particle density that can interact dramatically with any object carrying its own magnetic field or generating its own plasma environment. Comets, it turns out, are surprisingly effective plasma generators. As solar radiation heats the nucleus and drives off volatiles, those gases become ionized by ultraviolet light and the solar wind. The result is a complex electrically active coma that can extend millions of miles from the nucleus, far enough to interact with structures in the solar wind long before the nucleus itself encounters them. What makes comet plasma particularly interesting is its dust content. Unlike the relatively clean plasma environments around planets, cometary comedic particles of rock, metal, and organic compounds. This creates what plasma physicists call a dusty plasma, a fourth state of matter, where charged dust grains can dramatically alter the behavior of ions and electrons. Dusty plasmas exhibit nonlinear responses to external forces, can generate their own electric fields, and sometimes behave in ways that seem to violate the simple rules of magnetohydrodynamics. When SWAN erupted on September 26th, it wasn't just getting brighter. It was transforming from a relatively simple gas and dust cloud into an active plasma environment capable of interacting with the solar wind in complex ways. The sudden increase in mass loading, the technical term for adding new material to the solar wind flow, could theoretically create localized disturbances that propagate both upstream toward the Sun and downstream toward the outer solar system. The observational evidence for SWAN's transformation was unmistakable. Photographs taken before and after the outburst showed not just increased brightness, but changes in the tail's morphology. The ion tail, that blue-white streamer of electrically charged particles, had become more pronounced and structured. Dust lanes within the coma appeared more defined. Most tellingly, the tail's position angle had shifted slightly, suggesting that new gas and dust were being expelled from different regions of the nucleus. For amateur astronomers in the southern hemisphere, SWAN's outburst created an unexpected viewing opportunity. The comet's low southern declination made it challenging to observe from northern latitudes, but observers in South America, southern Africa, and Australia found themselves with front-row seats to a cosmic light show. Images flooded social media and astronomy forums, documenting the comet's rapid evolution in real time. But SWAN's awakening raises uncomfortable questions. Cometary outbursts are common enough. Comet Hale-Bopp produced dozens during its 1997 apparition, and Comet Lovejoy's 2011 sun-grazing encounter created a series of dramatic eruptions. What makes SWAN's timing noteworthy is its proximity to other high-energy events in the solar system. The nova explosions that had occurred just days earlier represent some of the most energetic phenomena in our galaxy. When a white dwarf star accretes enough material from a companion to trigger a thermonuclear explosion on its surface, the resulting blast can briefly outshine an entire galaxy. The high-energy photons produced by these explosions, gamma rays and X-rays, carrying millions of electron volts of energy, travel at the speed of light, and can reach Earth and the inner solar system within days or weeks. Could such radiation have contributed to SWAN's outburst? The energy flux from distant novae at Earth's distance is minuscule compared to solar radiance, but comets are exquisitely sensitive to even small changes in their thermal environment. A slight increase in heating could potentially trigger the sublimation of fresh volatile materials, particularly if the nucleus contains reservoirs of hypervolatile compounds like carbon monoxide or nitrogen. The physics remains speculative, but the timing is undeniably intriguing. Two stellar explosions flood the inner solar system with high-energy radiation. Days later, a comet suddenly erupts in brightness and activity, and then, as if responding to some invisible signal, the sun itself explodes with its most powerful flare in months. Coincidence? Possibly. But, as we'll see, the sun's response to SWAN's awakening suggests something far more complex, maybe unfolding in the electromagnetic soup that surrounds our star. Part 3. The sun fires back. If the universe has a sense of dramatic timing, it demonstrated that quality perfectly on September 28th at 0843 UTC, exactly 48 hours and 43 minutes after SWAN's mysterious outburst began. The sun responded with devastating precision. Active region 4232. A complex sunspot group that had been quietly simmering on the sun's eastern limb suddenly exploded. The M6-4 solar flare that erupted from this magnetic tangle released more energy in 10 minutes than humanity has produced in its entire history. X-ray detectors aboard the geostationary operational environmental satellites recorded the event as an R2-level radio blackout, powerful enough to disrupt high-frequency communications across the sunlit hemisphere of Earth. But the flare was just the opening act. Within hours, coronagraph instruments aboard the Solar and Heliospheric Observatory captured something far more ominous: a coronal mass ejection, a billion-ton bubble of magnetized plasma exploding outward from the sun at nearly 2 million miles an hour. The geometry of this eruption tells a story that should make any astronomer pause. Active region 4232 was positioned on the sun's eastern limb, approximately 60 degrees from the Sun-Ear line. This placed it in an interesting alignment with the orbital plane where SWAN was traveling. While the CME wasn't Earth-directed, the fact that likely spared our planet from significant geomagnetic disturbance, its trajectory appeared to intersect the region of space where the comet would be located in the coming days. Understanding CME propagation requires thinking in 3 dimensions. The sun rotates every 27 days, carrying active regions across its visible disk, like weather systems across Earth's surface. When a CME erupts, it doesn't travel in a straight line, but follows the complex magnetic field lines and plasma flows of the solar wind. These structures spiral outward from the sun, like water from a rotating garden sprinkler, creating the interplanetary magnetic field that fills the space between worlds. For SWAN, traveling at approximately 30 kilometers per second in its orbit around the sun, the approaching CME represented a potential direct hit. The comet's location, on September 28th, placed it roughly 40 million miles from the sun, well within the range where CMEs maintain their coherence and magnetic strength. If the timing and geometry worked out correctly, the shock front of the eruption could reach SWAN's position within 2 to 3 days. This scenario has played out before with spectacular results. In 2007, Comet ENK provided astronomers with a perfect natural experiment when a CME struck its iron tail directly. The stereo spacecraft captured the encounter in unprecedented detail, showing how the CME's magnetic field and high-velocity particles literally severed Encke's tail from its nucleus. Within hours, the disconnected tail material was swept away by the solar wind, while new gas continued to stream from the nucleus, gradually rebuilding what had been destroyed. The physics behind such tail disconnections reveals the intimate relationship between comets and the solar wind. A comet's ion tail forms when solar ultraviolet radiation ionizes gases in the coma, creating charged particles that become coupled to the sun's magnetic field. These ions are then accelerated away from the nucleus by the solar wind, forming the characteristic straight blue-white tail that can extend millions of miles into space. When a CME encounters this delicate structure, several things can happen. If the CME carries a strong southward-pointing magnetic field opposite to the field embedded in the tail, magnetic reconnection can occur. This process, similar to the mechanism that triggers aurora displays in Earth's atmosphere, can explosively reconfigure the magnetic field lines and sever the connection between the tail and the nucleus. Alternatively, the enhanced ram pressure from the CME's high-velocity particles can simply overpower the magnetic forces holding the tail together, shredding the structure like wind tearing through smoke. In either case, the result is dramatic. The comet's magnificent tail can disappear within hours, leaving behind a naked nucleus that must begin the slow process of rebuilding its plasma envelope. For SWAN, positioned directly in the path of the September 28th CME, such an encounter would be visible from Earth as a sudden change in the tail's brightness, morphology, or position angle. Experienced comet observers know to watch for these disconnection events during periods of high solar activity, as they provide real-time evidence of the invisible forces that shape our solar system. But the timing of the September 28th flare raises questions that extend beyond simple comet-CME interactions. The 48-hour delay between SWAN's outburst and the solar eruption falls within the range of light travel time from the comet's position to the Sunday. Could the sudden increase in SWAN's plasma output, the enhanced mass loading from its explosive outgassing, have somehow triggered instabilities in the solar corona? Mainstream helophysics would say no. The Sun contains 86% of the solar system's mass, and the energy output from a single comet represents a negligible perturbation to stellar processes. Active, region 4232, had been building magnetic tension for days, and its eventual eruption was likely inevitable, regardless of any external influences. Yet, the precision of the timing demands attention. Statistical analysis of comet flare correlations over the past several solar cycles might reveal whether such apparent synchronizations occur more often than chance would predict. The challenge lies in defining what constitutes meaningful correlation across the vast scales of space and time involved. What we can observe directly is the CME's continued propagation outward from the Sunday. Computer models, based on the solar wind prediction system, suggest the shock front should reach the outer solar system by early October, potentially sweeping through the orbital zones, where both SWAN and the mysterious interstellar visitor 3II Atlas are traveling. For observers on Earth, the next few days will reveal whether SWAN's encounter with this solar tsunami produces the dramatic tail disconnection events that have made comet-CME interactions among the most spectacular phenomena in space weather. The answer may also provide clues about whether we're witnessing an elaborate cosmic coincidence or the first evidence of feedback mechanisms that couple distant objects to our Sun in ways we're only beginning to understand. As September turns to October, the stage is set for a celestial collision that could illuminate the invisible networks of energy and information that bind our solar system together. The question is whether we're prepared to recognize the signals when they arrive. Part 4. The Geometry of Power, October 21st, 2025. Mark this date on your calendar, because the cosmos has arranged a configuration that occurs perhaps once in a human lifetime. On this day, 3 separate celestial events converge with mathematical precision that would make ancient astronomers reach for their most sacred texts. SWAN achieves its closest, the approach to Earth, a mere 0.2606 astronomical units, or roughly 10 million miles. The Moon enters its new phase, creating the darkest possible skies for observation, and hiding behind the Sun's glare, invisible to Earth-based telescopes, the interstellar visitor 3I Atlas continues its approach toward perihelion, scheduled for October 30th, at just 1.4 astronomical units from our star. This isn't astrology. This is orbital mechanics, revealing the hidden clockwork that governs our cosmic neighborhood. But sometimes, orbital mechanics produces coincidences so precise, they feel choreographed by an intelligence we can barely comprehend. Both SWAN and 3E Atlas are traveling close to the ecliptic plane, that imaginary disk where Earth and most other planets orbit the Sunday. This positioning places both objects within the most magnetically active region of interplanetary space, where the heliospheric current sheet creates a complex landscape of electromagnetic boundaries and particle acceleration zones. The heliospheric current sheet deserves special attention because it's here that the Sun's influence becomes most complex and interesting. Picture a vast rotating disk of electrically charged particles, extending billions of miles outward from the Sunday. As our star rotates every 27 days, this disk develops wrinkles and folds, creating a structure that resembles a spinning ballerina's skirt made of plasma and magnetic field lines. Objects traveling through this environment don't simply follow gravitational trajectories. They become embedded in the Sun's extended electromagnetic field, subject to forces and interactions that can alter their behavior in subtle but measurable ways. Comets, with their extensive plasma tails and electrically active comets, are particularly sensitive to these influences. When multiple large objects travel through the same region of the current sheet within a short time period, theoretical possibilities emerge that haven't been extensively studied. Could the combined plasma output from outgassing comets locally alter the current density of the heliospheric circuit? Might such alterations propagate back toward the Sun, potentially influencing the stability of active regions in the corona? These questions venture into speculative territory, but they're not entirely without precedent. The solar wind carries roughly 1 billion tons of material away from the Sun every year. Yet this enormous mass loss is precisely balanced by the Sun's gravitational and magnetic forces. Any additional mass loading, even from comets, must be accommodated by the system somehow. The toy model works like this. Imagine the heliospheric current sheet as a vast electrical circuit with the Sun as the primary generator and the outer heliosphere as the load. Comets embedded in this circuit act like variable resistors, their plasma output changing as they heat up and cool down during their orbits. Under normal circumstances, individual comets contribute negligible changes to the circuit's overall behavior. But what happens when multiple large objects simultaneously increase their plasma output while traveling through the same current sheet layer? Could their combined influence create measurable perturbations that propagate toward the Sun at the speed of light, potentially arriving at active regions just as those regions approach magnetic instability? The physics remains highly speculative, and any effects would likely be subtle compared to the Sun's intrinsic variability. Solar wind inertia dwarfs cometary outputs by many orders of magnitude. Yet plasma physics is notorious for producing non-linear responses where small inputs can trigger large outputs under the right conditions. Consider the Carrington event of 1859. the most powerful geomagnetic storm in recorded history. That catastrophic space weather event began with a relatively modest coronal mass ejection that happened to occur at precisely the moment when Earth's magnetosphere was in an unusually sensitive state. The result was aurora visible as far south as the Caribbean and telegraph systems catching fire across North America. The lesson is clear. In complex systems, timing matters as much as magnitude. A small input applied at exactly the right moment can trigger cascading effects that propagate throughout the entire system. For the October 21st convergence, the timing appears almost suspiciously precise. The new moon eliminates lunar interference, creating optimal viewing conditions for any changes in SWAN's tail morphology. The comet's close approach to Earth maximizes the angular resolution available to ground-based telescopes, and 3 Atlas's position near solar conjunction places it in the most electromagnetically active region of the inner solar system. From a purely observational standpoint, this geometry offers unprecedented opportunities to study comet-solar-wind interactions in real time. Ground-based observers will have excellent views of SWAN's tail structure, just as it encounters any shock waves or magnetic discontinuities propagating outward from recent solar activity. Space-based coronagraphs will capture the region around 3I Atlas as it experiences peak solar heating. But the geometry also raises deeper questions about the nature of coincidence itself. In a solar system containing billions of objects following independent gravitational trajectories, mathematical chance predicts that remarkable alignments will occasionally occur. The challenge lies in distinguishing between meaningless coincidences and configurations that reveal previously hidden aspects of how our cosmic environment actually works. If the October 21st configuration represents mere chance, we should expect to observe ordinary comet behavior, modulated by routine solar wind variations. SWAN might show some tail disconnection events if it encounters CME shock fronts, but nothing beyond what's been documented hundreds of times before. If, however, the configuration represents something more significant, a resonance condition where multiple objects embedded in the same electromagnetic environment can collectively influence solar activity, then we might observe correlations that challenge our understanding of cause and effect in the solar system. The answer lies in the data we'll collect over the coming weeks. Coronagraph images, plasma measurements, and ground-based observations will either support or refute the possibility that our solar system operates as a more tightly coupled electromagnetic machine than current models suggest. Either outcome advances human knowledge, but one outcome might also force us to reconsider our place in a universe that may be far more interconnected than we ever dared imagine. Part 5. Energy in motion from nova to CME. The sequence reads like a cosmic detective story written in the language of electromagnetic radiation and plasma physics. 2 distant stellar explosions flood the inner solar system with high-energy photons. A comet suddenly erupts in brightness and activity. The sun responds with its most powerful flare in months. The timing is so precise, it demands investigation, even if that investigation leads us into territories where speculation must be carefully separated from established science. Let's reconstruct the timeline with forensic precision. Nova 5, 7994. Sagittari blazed to life. In late September, its thermonuclear explosion, briefly outshining thousands of normal stars. Days later, Nova 51935 Centauri followed suit, adding its own contribution to the flux of high-energy radiation washing across our solar system. Both events were detected by gamma-ray and X-ray observatories, confirming that these weren't ordinary stellar flares, but genuine nova explosions, white dwarf stars accreting material from companion stars until critical density triggered runaway fusion reactions. The energy involved in such explosions defies human comprehension. In a matter of hours, A nova can release more energy than our Sun will produce over millions of years. The gamma rays and X-rays produced by these thermonuclear detonations carry millions of times more energy per photon than visible light, capable of ionizing atoms and driving chemical reactions across vast distances of space. When these high-energy photons reached the inner solar system, traveling at light speed and arriving within days of the initial explosions, they encountered a complex environment of planets, asteroids, comets, and the Sun itself. For most objects, the additional energy flux represented a negligible change compared to normal solar radiation. But comets, with their pristine surfaces and volatile rich compositions, might be expected to show more sensitivity to even small perturbations in their energy balance. The conservative physics is clear. Photon fluxes from distant nova are minuscule compared to the Sun's output. Even the most powerful nova explosion, viewed from distances of thousands of light-years, delivers energy densities at Earth that are billions of times smaller than normal sunlight. Any direct causal relationship between nova radiation and SWAN, September 26th outburst, would require physical mechanisms that simply don't exist in our current understanding of how electromagnetic radiation interacts with cometary materials. Yet the timing correlation persists, demanding at least theoretical consideration of possible pathways. Could high-energy photons somehow trigger processes in cometary nuclei that aren't captured by simple radiative heating models? Gamma rays and X-rays can penetrate much deeper into solid material than visible light, potentially reaching subsurface layers where different volatile compounds might be stored. Could such deep heating create pressure buildups that eventually lead to explosive outgassing? The energetic chain hypothesis, while highly speculative, provides a framework for thinking about possible connections. Nova radiation perturbs subsurface volatile reservoirs in comets throughout the inner solar system. This leads to enhanced outgassing and increased plasma production. As affected comets heat up, the additional mass loading alters local properties of the solar wind and heliospheric current sheet. These changes propagate toward the Sun and, under precisely the right conditions, influence the magnetic stability of active regions approaching eruption threshold. Each link in this hypothetical chain faces significant physical obstacles. Nova radiation intensity drops with the square of distance, making effects at cometary distances extremely weak. Cometary outgassing rates depend primarily on solar heating, which vastly dominates any external radiation sources. Solar wind mass loading from comets represents a negligible fraction of the total particle flux. An active region evolution follows its own complex magnetic dynamics that appear insensitive to small external perturbations. Testing such a chain requires observational strategies that can distinguish genuine physical connections from the illusion of correlation created by coincidental timing. If nova to comet to solar coupling represents a real physical process, it should produce detectable signatures that persist across multiple events and objects. What would falsify the energetic chain hypothesis? If SWAN's outburst began before the nova peaks occurred, temporal causality would be violated. If subsequent CMEs show no correlation with comet positions or activities, the solar connection fails. If in situ solar wind measurements reveal no anomalies during periods of supposed electromagnetic coupling, the mechanism lacks empirical support. Historical analysis provides another testing ground. The past 2 solar cycles have witnessed dozens of nova explosions, hundreds of cometary outbursts, and thousands of solar flares and CMEs. If energetic chains represent genuine physical processes rather than rare coincidences, statistical analysis should reveal timing biases that exceed random chance. The challenge lies in defining appropriate statistical tests. Comets outburst for many reasons: seasonal heating, structural weakness, collision with debris, or simple stochastic processes in their sublimation dynamics. Solar flares follow their own complex patterns related to magnetic field evolution and active region development. Nova occur according to the binary star physics of white dwarf accretion, completely independent of solar system conditions. Finding meaningful correlations among such disparate phenomena requires careful attention to multiple testing corrections and selection biases. The human brain excels at finding patterns in random data, particularly when those patterns support compelling narratives about cosmic connection and universal harmony. Yet, dismissing the September sequence as pure coincidence may be premature. Science advances by taking interesting correlations seriously, while maintaining appropriate skepticism about causal interpretations. The key lies in developing testable predictions that can be confirmed or refuted by future observations. If energetic chains represent real physics, they should produce repeatable signatures as new comets encounter similar conditions. The coming weeks, with SWAN approaching Earth and 3 Atlas approaching perihelion, provide an opportunity to test whether apparent correlations between distant energy sources and local solar system dynamics to represent genuine coupling, or merely the tendency of human consciousness to find meaning in mathematical coincidence. The universe has presented us with an intriguing puzzle. The solution will emerge from careful observation, rigorous analysis, and the kind of intellectual honesty that acknowledges both the beauty of cosmic synchronicity and the stern requirements of scientific evidence. Part 6. The Plasma Bridge Hypothesis. Deep in the mathematics of plasma physics lies a possibility so elegant and disturbing that mainstream heliphysics has largely ignored it for decades. The idea suggests that comets might function as more than passive objects heated by the sunday. They could serve as transient electrodes in a vast solar system circuit capable of modulating electromagnetic flows across millions of miles of space. This is the plasma bridge hypothesis, and it traces its intellectual lineage to Hannes Alfvén, the Swedish physicist who won the Nobel Prize for developing the mathematical foundations of magnetohydrodynamics. Alfvén recognized that space, far from being empty, contains a complex medium of charged particles and magnetic fields that can carry electrical currents and store electromagnetic energy across astronomical distances. In Alfvén's view, the solar system resembles a gigantic electrical circuit. The Sun acts as a central generator, producing charged particles and magnetic fields that flow outward at nearly 2 million miles per hour. This solar wind carries embedded electrical currents that connect the Sun to planets, asteroids, comets, and the boundary of interstellar space some 11 billion miles away. Most objects in this circuit act as passive loads. They absorb energy and particles from the solar wind without significantly affecting the overall current flow. But comets, Alfvén realized, might be different. Their ability to suddenly produce massive amounts of gas and plasma during outbursts could temporarily alter the electrical properties of their local environment, potentially creating feedback effects that propagate throughout the circuit. The mechanism involves what plasma physicists call double layers, regions of space where positive and negative charges separate, creating strong electric fields that can accelerate particles and drive currents. When a comet outbursts, and that produces a dense cloud of ionized gas, this plasma can organize itself into complex electrical structures that interact with the solar wind in nonlinear ways. Unlike the relatively clean plasma environments around planets, cometary comets contain vast quantities of dust particles that become electrically charged through interactions with solar radiation and the solar wind. This creates what's known as a dusty plasma, a fourth state of matter where microscopic particles can carry substantial electrical charge and dramatically alter the behavior of ions and electrons. Dusty plasmas exhibit fascinating properties that violate many of the assumptions underlying conventional magnetohydrodynamics. They can form self-organizing structures, generate their own electric fields, and respond to external forces in ways that seem to defy simple physical intuition. Laboratory experiments have shown that dusty plasmas can create rotating spirals, propagating waves, and even structures that resemble biological cells or neural networks. When applied to comets, these properties suggest that outbursting nuclei might create temporary plasma structures capable of interacting with solar wind currents in complex ways. If such structures form near the heliospheric current sheet, that vast boundary layer where the sun's magnetic field changes polarity, they could theoretically influence the propagation of electromagnetic disturbances across the solar system. The heliospheric current sheet deserves special attention because it represents the solar system's most electrically active region. Here, magnetic field lines from opposite solar poles meet and reconnect, creating zones of enhanced particle acceleration and current flow. Objects traveling through these zones experience rapid changes in their electromagnetic environment that can trigger dramatic responses in their plasma tails and comet. SWAN's trajectory keeps it traveling close to the ecliptic plane, maximizing its exposure to current, sheet crossings, and magnetic discontinuities. When the comet outbursted on September 26th, it wasn't just getting brighter. It was potentially transforming into an active electrode, capable of altering local current flow patterns in ways that might propagate back toward the evidence requirements for plasma bridges are demanding. Genuine electromagnetic coupling between comets and solar activity would produce correlations in particle spectra, radio emissions, and magnetic field measurements that persist across multiple events and objects. We would expect to see repeatable timing relationships between comet outbursts and solar flares, particularly when comets are positioned near current sheet boundaries. Unfortunately, the observational tools needed to test these predictions are limited. We lack in situ plasma measurements at SWAN's location, forcing us to rely on remote sensing and computer modeling to infer what might be happening in the comet's immediate environment. The Parker Solar Probe and other space missions provide excellent data about solar wind conditions near Earth, but extrapolating those measurements to comet locations requires sophisticated modeling that introduces significant uncertainties. Historical precedents do exist for dramatic comet-solar wind interactions. The 2007 encounter between comet ENK and a coronal mass ejection provided unambiguous evidence that solar disturbances can sever cometary tails and reorganized plasma structures around comet nuclei. Stereo spacecraft captured the entire event, showing how magnetic reconnection could explosively reconfigure the comet's electromagnetic environment within hours. But Anchor's tail disconnection represented a one-way interaction. The CME affected the comet, not the reverse. Evidence for feedback from comets to solar activity remains elusive, relegated to the realm of theoretical possibility rather than observational fact. The plasma bridge hypothesis makes specific predictions for the October convergence period. If SWAN and 3I Atlas are capable of influencing solar activity through electromagnetic coupling, we should observe correlations between their positions, activities, and solar flare production that exceed random chance. Radio telescopes might detect coherent emissions associated with current flows between comet positions and solar active regions. Particle detectors could measure anomalous populations of energetic particles that trace back to cometary sources. Alternatively, the hypothesis might be completely wrong. The energy scales involved in solar activity dwarf cometary contributions by many orders of magnitude, making feedback effects implausibly small. The apparent correlations between comet outbursts and solar flares might represent nothing more than coincidental timing amplified by human pattern recognition. Either outcome advances our understanding of how electromagnetic energy flows through the solar system, but if plasma bridges prove real, they would reveal our cosmic neighborhood as a far more tightly coupled and responsive system than current models suggest. A living circuit where information and energy flow in both directions between the Sun and its most distant children. The coming weeks will provide crucial tests of whether such coupling represents physical reality or merely the human tendency to find connection in cosmic coincidence. Part 7. The Historical Precedent. Oumuamua and the 2017 Mexico quake. Sometimes the universe arranges events with such precise timing that even the most skeptical scientists pause to wonder if coincidence alone can explain what they're witnessing. September 2017 provided one of those moments, a convergence of cosmic violence and terrestrial catastrophe that continues to challenge our understanding of cause and effect across the solar system. The sequence began on September 6th with an X9 free solar flare, one of the most powerful eruptions ever recorded from our Sunday. The explosion sent a massive coronal mass ejection racing toward Earth at over 4 million miles per hour, triggering severe geomagnetic storms and aurora displays visible as far south as Alabama. But this was merely the opening act in a drama that would unfold over the following week with mathematical precision. 3 days later, on September 9th, the interstellar visitor Oumuamua, the first confirmed object from beyond our solar system, reached perihelion at just 25 million miles from the Sunday. This elongated, tumbling asteroid had been traveling through interstellar space for millions of years, before gravity captured it in a hyperbolic trajectory that brought it closer to our star than Mercury's orbit. The timing seemed remarkable enough, but the universe wasn't finished with its demonstration of synchronized destruction. On September 10th, just 24 hours after Oumuamua's closest solar approach, the Sun erupted again, with an X8-2 flare, the second most powerful solar explosion of the entire solar cycle. The back-to-back X-class events created a sustained period of extreme space weather that bombarded Earth's magnetosphere with high-energy particles and electromagnetic radiation for days. Then, as if responding to some invisible signal propagating from space to Earth, the planet itself began to shake. September 8th. Right between the two massive solar flares, and coinciding almost exactly with Oumuamua's perihelion passage, an 8.2 magnitude earthquake devastated the isthmus of Tehuantepec in southern Mexico. The quake, centered near the town of Piji, Japan, in Chiapas state, generated tsunami warnings across the Pacific and was felt as far away as Mexico City, nearly 400 meters from the epicenter. The statistical improbability of this timing sequence is difficult to overstate. Major earthquakes with magnitudes exceeding 8 occur roughly once per year globally. X-class solar flares happen perhaps 5 to 10 times per solar cycle. Interstellar objects reach perihelion in our solar system, perhaps once per human lifetime. The probability of all three phenomena occurring within a 4-day window purely by chance approaches astronomical odds. Yet the United States Geological Survey maintains its position with unwavering certainty. No demonstrated causal relationship exists between space weather events and seismic activity on Earth. Earthquakes result from the release of tectonic stress along fault systems driven by the slow motion of continental plates and the cooling of Earth's interior. Solar flares and geomagnetic storms, while capable of affecting satellite communications and power grids, lack any known mechanism for triggering seismic events. This official stance reflects decades of careful statistical analysis, showing no significant correlations between solar activity and earthquake occurrence. Researchers have examined thousands of seismic events, spanning multiple solar cycles, looking for evidence that geomagnetic storms or cosmic ray variations might influence the timing of major quakes. The overwhelming conclusion is that earthquakes follow their own complex patterns related to geological processes that operate independently of space weather. But alternative research communities have reached different conclusions. Studies published in peer-reviewed journals have documented statistical relationships between atmospheric and ionospheric anomalies and subsequent earthquake activity. These lithosphere, atmosphere, ionosphere coupling models suggest that electrical and electromagnetic processes might play previously unrecognized roles in seismic phenomena. The proposed mechanisms involve the buildup of electrical charge in stressed rock formations, potentially creating electromagnetic signatures that propagate upward through the atmosphere to the ionosphere. Satellites have detected unusual electromagnetic emissions and ionospheric perturbations hours or days before some major earthquakes, leading researchers to investigate whether external electromagnetic influences might affect the timing of seismic events in fault systems already approaching failure. If such coupling mechanisms exist, periods of intense geomagnetic activity, like those triggered by X-class solar flares, could theoretically influence the electrical state of Earth's upper atmosphere and ionosphere in ways that might affect seismic processes. The energy scales involved remain problematic for direct causation, but complex systems sometimes exhibit threshold effects, where small inputs can trigger large responses if applied at precisely the right moment. The 2017 Mexico sequence provides a natural experiment for testing these ideas. The Tehuantepec earthquake occurred in a region of known tectonic activity, where the Cocos Plate subducts beneath the North American plate. Stress had been building along this fault system for decades, making a major earthquake statistically likely within any given year. The question is whether the intense space weather conditions surrounding UMWAM's perihelion passage might have influenced the precise timing of the seismic release. Answering this question requires careful analysis of multiple datasets. Researchers would need to examine ionospheric measurements from the days preceding the earthquake, looking for anomalies that correlate with the solar flare timing. Magnetic field observations from ground-based magnetometers might reveal signatures of enhanced electromagnetic activity in the earthquake preparation zone. Statistical analysis of global seismic patterns during other periods of extreme space weather could help determine whether the Mexican event represents a genuine correlation or merely coincidental timing. The challenge lies in distinguishing real physical relationships from the human tendency to find patterns in random data. Large earthquakes are traumatic events that capture public attention and remain vivid in memory long after smaller, more frequent tremors are forgotten. Similarly, dramatic space weather events like X-class flares generate widespread media coverage that makes them seem more common and significant than they actually are. When memorable events cluster together in time, our pattern-seeking brains naturally construct causal narratives that may have no basis in physical reality. The key to avoiding such false correlations lies in rigorous statistical analysis that accounts for the multiple comparisons, problem, and selection biases inherent in post hoc pattern recognition. Yet completely dismissing the 2017 sequence as pure coincidence may be premature. Science advances by taking interesting correlations seriously while maintaining appropriate skepticism about causal interpretations. The convergence of interstellar visitor, solar maximum conditions, and major seismic activity provides a unique case study for testing hypotheses about electromagnetic coupling between space weather and terrestrial phenomena. As we approach the October 2025 convergence of SWAN, 3 Atlas, and enhanced solar activity, the 2017 precedent offers both cautionary lessons and intriguing possibilities. If electromagnetic coupling between cosmic events and terrestrial responses represents genuine physics, we might expect to observe similar patterns during periods of comparable space weather intensity. The coming weeks will provide opportunities to test whether the Mexican earthquake sequence reflects meaningful physical relationships or merely the kind of striking coincidence that makes conspiracy theorists of us all. Either outcome will advance our understanding of how energy and information flow between the cosmic and terrestrial domains of human experience. Part 8. The Forgotten Solar Mysteries. Hidden in the archives of space-based observations lie encounters so dramatic they rewrote textbooks, yet somehow faded from public consciousness as new emissions captured headlines. These forgotten episodes reveal the sun's capacity for precision violence and provide crucial context for understanding what might unfold as October's celestial convergence approaches. Comet Encke's 2007 encounter with a coronal mass ejection stands as perhaps the most spectacular comet-solar interaction ever captured by human instruments. The stereo spacecraft, positioned to provide stereoscopic views of the sun's corona, he recorded the entire drama in unprecedented detail as a billion-ton plasma bubble traveling at 3 million miles an hour obliterated the comet's magnificent iron tail in a matter of hours. The sequence began routinely enough. ENK, a short-period comet that returns to the inner solar system every 3.3 years. It was approaching perihelion and developing the characteristic blue-white iron tail that forms when solar ultraviolet radiation ionizes gases streaming from the nucleus. This tail, composed primarily of carbon monoxide and water vapor ions, extended millions of miles behind the comet as charged particles became coupled to the sun's magnetic field. Then the CME struck with surgical precision. Stereo's cameras captured the moment of impact as the shock front, a wall of magnetized plasma, moving faster than the speed of sound in the solar wind, engulfed Encke's delicate tail structure. Within hours, magnetic reconnection had severed the connection between the tail and the nucleus, leaving behind a ghostly streamer of ionized gas that was quickly swept away by the enhanced solar wind flow. But Encke's nucleus continued producing new gas and dust, gradually rebuilding what the CME had destroyed. Time-lapse movies from Stereo show the comet's tail slowly reforming over the following days, like a phoenix rising from electromagnetic ashes. The entire episode provided unambiguous proof that solar disturbances could dramatically reorganize cometary plasma structures through direct electromagnetic coupling. 7 years later, Comet Siding Spring provided an even more extraordinary demonstration of how comets can reshape planetary environments. This Oort cloud visitor, following a million-year orbit that brought it within 87,000 meters of Mars, engulfed the red planet in its extended coma and triggered the most intense meteor shower in Martian history. NASA's MAVEN spacecraft, designed to study Mars's upper atmosphere, found itself in the unique position of flying directly through a comet's coma while monitoring the planet's ionospheric response. The results exceeded all expectations. Siding Spring's dust and gas dramatically altered Mars's atmospheric chemistry, depositing metallic ions throughout the upper atmosphere and creating ionospheric disturbances that persisted for days after the encounter. The energy deposition was substantial enough to heat Mars' upper atmosphere by several hundred degrees, demonstrating that comets carry sufficient material and energy to measurably affect planetary systems. If a comet could so dramatically influence Mars's thin atmosphere, the implications for electromagnetic coupling with the much more massive and magnetically active Sun became impossible to ignore. These encounters reveal comets as far more than passive chunks of ice and rock. They function as dynamic, electrically active objects capable of dramatically altering their electromagnetic environment and the behavior of other objects they encounter. When embedded in the solar wind and heliospheric current sheet, Outgassing comets become temporary plasma sources that can locally reorganize magnetic field lines and particle flows across millions of miles of space. The conductive probe metaphor, while speculative, provides a useful framework for thinking about how comets might sample and potentially influence the electrical state of interplanetary space. As they travel through regions of varying magnetic field strength and polarity, comets experience changing electromagnetic environments that affect their plasma production and tail morphology. These changes in turn might influence local current flow patterns in ways that could theoretically propagate back toward their source. Mainstream helophysics remains appropriately cautious about claims of comet-to-sun feedback, emphasizing that the energy scales involved in solar activity dwarf cometary contributions by many orders of magnitude. The sun's magnetic field contains enough energy to power human civilization for millions of years. While even the largest comet represents a negligible perturbation to stellar scale processes, yet plasma physics is notorious for producing non-linear responses, where small inputs can trigger large outputs under precisely the right conditions. The key lies in understanding when and where such threshold effects might occur. Active regions in the solar corona can spend days or weeks building magnetic tension before erupting in spectacular flares and CMEs. During these build-up phases, coronal structures might theoretically become sensitive to small perturbations that would normally be insignificant. If comets embedded in the heliospheric current sheet can indeed influence local electromagnetic conditions, and if such influences can propagate toward the sun at the speed of light, then timing becomes crucial. A small perturbation, arriving at an active region just as it approaches magnetic instability, could theoretically trigger premature eruption, much like a small earthquake can trigger a devastating avalanche on a slope already loaded with unstable snow. Testing these ideas requires observational strategies that can distinguish genuine electromagnetic coupling from coincidental timing. We need coordinated observations of comet positions, activities, and plasma properties during periods of solar flare production combined with statistical analysis across many events to determine whether apparent correlations exceed random chance. The upcoming October convergence provides an opportunity to apply these observational strategies as SWAN approaches Earth and 3 Atlas reaches perihelion near the Sunday. If electromagnetic coupling between comets and solar activity represents genuine physics, the timing and geometry of this configuration should produce detectable signatures in space weather data. Alternatively, the convergence might reveal nothing more than ordinary comet behavior modulated by routine solar wind variations. Either outcome advances scientific understanding, but one outcome might also force us to reconsider the fundamental nature of electromagnetic relationships within our solar system. The forgotten mysteries of Encare and Siding Spring remind us that space remains full of surprises for those prepared to look beyond conventional assumptions about how cosmic objects interact. As October approaches, we may be about to witness another chapter in this continuing story of electromagnetic drama played out across the vast stage of interplanetary space. Part 9. The Nova-Solar Coupling Theory. In the vast library of astrophysical phenomena, few events release energy on scales that dwarf human imagination, quite like nova explosions. When a white dwarf star accretes enough material from a companion to trigger thermonuclear fusion on its surface, the resulting blast can briefly outshine an entire galaxy and flood nearby space with high-energy radiation that travels at the speed of light across interstellar distances. The 2 novae that erupted in late September 2025, V7994, Sagittari, and V11,935, Centauri represent exactly this type of cosmic violence. Both events were detected by gamma-ray and X-ray observatories as their high-energy emissions swept across the solar system, arriving at Brother Earth and the inner planets within days of the initial explosions. The timing of these arrivals just prior to SWAN's mysterious outburst and the subsequent solar flare creates a correlation that demands investigation, even if it leads into speculative territory. The skeptical case against nova-solar coupling is straightforward and compelling. Photon fluxes from distant stellar explosions, while carrying enormous total energy, are spread across vast spherical volumes of space by the time they reach our solar system. Even the most powerful nova explosion, viewed from distances measured in thousands of light-years, delivers energy densities at Earth that are billions of times smaller than normal sunlight. To put this in perspective, the total energy flux from both September novae combined, integrated over their entire duration, would be insufficient to power a single household light bulb for more than a few seconds. The idea that such minuscule energy additions could trigger major solar flares, events that release more energy than humanity has produced in its entire history, violates basic principles of energy conservation and proportional response. Yet, the physics of complex systems sometimes produces surprises that challenge intuitive notions about cause and effect. The key question isn't whether nova radiation carries enough energy to directly force solar eruptions, but whether it might influence delicate equilibria in ways that could affect the timing of events that would occur anyway due to internal solar dynamics. Active regions in the solar corona can spend days or weeks building magnetic tension through the complex interplay of plasma flows, magnetic field evolution, and thermal processes. During these build-up phases, coronal structures exist in states of marginal stability where small perturbations might theoretically advance or delay the timing of inevitable magnetic eruptions. High-energy photons from nova explosions possess properties that distinguish them from normal solar radiation. Gamma rays and X-rays can penetrate much deeper into plasma and solid matter than visible light, potentially reaching regions where different physical processes dominate. In the solar corona, such penetrating radiation might influence ionization states, heating rates, or magnetic reconnection processes in ways that aren't captured by models based solely on local solar heating. The fringe avenues for nova-solar coupling venture into territory where established physics gives way to speculative hypotheses that lack experimental support. Some researchers have proposed that neutrinos, nearly massless particles produced in vast quantities during thermonuclear explosions, might interact with solar plasma in ways that current models don't predict. Others suggest that high-energy photons could trigger cascades of particle interactions that amplify small initial perturbations into measurable effects. These ideas face enormous theoretical obstacles. Neutrino interaction cross-sections are so small that trillions of them pass through human bodies every second without causing any detectable effects. The probability of neutrinos from distant novae significantly affecting solar plasma processes approaches zero within current understanding of particle physics. A more modest possibility involves what cognitive scientists call synchrony illusions, the tendency of human pattern recognition to find meaningful connections between independent events that happen to cluster together in time. Solar rotation creates 27-day periodicities in active region evolution. The heliospheric current sheet exhibits similar periodicities in its magnetic structure. Comet orbital mechanics produces predictable timing patterns in when objects reach perihelion or maximum brightness. Observer visibility creates additional periodicities related to Earth's rotation and orbital motion. When multiple independent periodic processes interact, they can create apparent synchronizations that have no underlying physical basis. The challenge lies in distinguishing genuine causation from the mathematical inevitability that independent oscillators will occasionally fall into apparent phase relationships. If researchers wanted to test nova-solar coupling hypothesis rigorously, they would need to conduct statistical analyses across many events and solar cycles. The approach would involve cataloging all nova explosions detected over the past several decades, along with their precise timing, distances, and energy outputs. This database would then be compared with comprehensive records of solar flare activity, looking for timing correlations that exceed random chance after appropriate corrections for multiple comparisons. Such analysis would also need to account for selection biases inherent in human pattern recognition. Dramatic events like X-class flares and bright comets capture attention and remain vivid in memory, while smaller, more frequent events fade into statistical background. The tendency to remember striking coincidences while forgetting countless non-coincidences, and create false impressions of meaningful correlation where none exists. Monte Carlo simulations could help address these biases by generating thousands of random event sequences with the same statistical properties as real astronomical data, then testing whether apparent correlations in actual observations exceed what would be expected from pure chance. The interim verdict on nova solar coupling must remain one of watchful curiosity rather than confident acceptance or rejection. The energy scale arguments against direct causation are compelling, but complex systems sometimes exhibit threshold effects, where small inputs can trigger large responses under precisely the right conditions. As we approach the October convergence period with SWAN near Earth and 3 Atlas approaching perihelion, the solar system provides a natural laboratory for testing whether apparent correlations between distant energy sources and local solar activity represent genuine physics, or merely the human tendency to find meaning in mathematical coincidence. The coming weeks may reveal whether the September nova sequence represents the opening movement of a cosmic symphony, or simply another reminder that in a universe containing billions of energetic objects, remarkable coincidences are not only possible, but inevitable. Part 10. 3 Atlas, the enigma behind the Sunday. Somewhere in the glare of our star, invisible to Earth-based telescopes, lurks an object that challenges everything we thought we knew about visitors from interstellar space. 3I. Atlas, the third confirmed interstellar object ever detected, was discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System Survey in Chile. Since then, it has remained one of the most enigmatic and potentially significant astronomical discoveries of the 21st century. Unlike its predecessors, the elongated asteroid Oumuamua and the more comet-like 2Y Borisov 3I Atlas follows a hyperbolic trajectory that brings it to perihelion around October 30th at approximately 1.4 astronomical units from the Sunday. This places it just inside Mars's orbit at closest approach, making it the nearest interstellar visitor ever observed during its solar encounter. The geometry of 3I Atlas's current position creates both opportunities and challenges for observation. Throughout September and early October, the object maintains very low solar elongation, as seen from Earth, meaning it appears to travel close to the Sun's position in our sky. This makes direct observation extremely difficult, requiring specialized coronagraph instruments or space-based observatories to penetrate the solar glare. But what 3 Atlas lacks in visibility from Earth, it makes up for in accessibility to other observers. Mars-orbiting spacecraft find themselves in a unique position to study this interstellar visitor as it approaches perihelion. The European Space Agency has announced that several of their Mars and Jupiter missions are being tasked to observe 3I Atlas during its closest solar approach, potentially providing unprecedented data about an interstellar object's behavior in the inner solar system. The predicted closest approach to Mars occurs around October 3rd, when 3I Atlas will pass, within approximately 30 million kilometers. roughly 0.19 astronomical units, of the red planet. While this represents a substantial misdistance in human terms, it places Mars-based instruments within excellent range for spectroscopic analysis, dust detection, and monitoring of any outgassing or coma development, as the object experiences peak solar heating. Early observations of 3 Atlas have revealed characteristics that distinguish it from previous interstellar visitors. Preliminary reports suggest the object may be developing a more substantial coma, the cloud of gas and dust that surrounds active comet nuclei, than was observed around 2I Boris during its 2019 passage through the inner solar system. However, these observations remain preliminary and subject to the challenging observing conditions created by the object's low solar elongation. The hidden colossus hypothesis, while highly speculative, captures the imagination of researchers trying to understand what 3I Atlas might represent. If the object contains substantial quantities of hypervolatile materials like carbon monoxide or nitrogen, compounds that sublime readily, even at large distances from the Sun, it could potentially develop an enormous coma as it approaches perihelion. Such a coma might extend millions of miles from the nucleus, creating a substantial obstacle to solar wind flow and a potentially significant source of plasma loading in the inner heliosphere. The physics of such interactions ventures into largely unexplored territory. Previous interstellar visitors have been relatively small objects with minimal outgassing, providing little opportunity to study how interstellar materials interact with our solar wind environment. If 3I Atlas proves to be a more substantial object with significant volatile content, it could create the first opportunity to observe how interstellar matter integrates with and potentially influences solar system plasma dynamics. The interstellar capacitor metaphor, while romantic in its implications, reflects genuine questions about how objects carrying the electromagnetic signature of interstellar space might interact with the heliosphere's magnetic field structure. Interstellar space contains magnetic fields, cosmic rays, and plasma densities that differ significantly from conditions within the solar wind's domain of influence. When interstellar objects enter the heliosphere, they potentially carry information about these external conditions embedded in their magnetic and electrical properties. Testing these speculative ideas requires observational strategies that can measure properties currently beyond the reach of most instruments. Spectroscopic analysis could reveal the composition of any developing coma, particularly the presence of hypervolatile species that would indicate substantial outging potential. Polarimetric observations might detect dust-size distributions and particle properties that differ from solar system materials. Radio observations could search for coherent emissions associated with plasma interactions between the object and the solar wind. The challenge lies in distinguishing genuine physical signatures from observational artifacts and instrumental limitations. 3 Atlas's low solar elongation creates substantial challenges for ground-based observations. While space-based instruments capable of penetrating solar glare have limited opportunities for detailed spectroscopic analysis, NASA's current stance on 3I Atlas reflects appropriate scientific caution about overclaiming significance without peer-reviewed observational constraints. Early media reports have varied widely in their estimates of the object's size, composition, and activity level, highlighting the difficulty of extracting reliable information from challenging observational conditions. What remains testable includes the object's non-gravitational accelerations, tiny changes in orbital motion that would indicate outgassing forces acting on the nucleus. Previous interstellar visitors have shown measurable non-gravitational effects, confirming their active nature despite their exotic origins. If 3 Atlas exhibits similar behavior, it would provide additional evidence for substantial volatile content and outgassing potential. The European Space Agency's decision to target multiple spacecraft toward 3I Atlas observations represents a significant investment in understanding this unique visitor. Mars Express, the ExoMars Trace Gas Orbiter, and potentially the Jupiter Icy Moons Explorer could all contribute observations during the object's closest solar approach. These coordinated measurements might provide the first comprehensive dataset on an interstellar object's behavior during peak solar heating. As October approaches and 3 Atlas nears perihelion, the convergence with SWAN's closest Earth approach creates an unprecedented opportunity to study two very different types of solar system visitors during their most active phases. Whether this timing represents meaningful physical synchronization or pure astronomical coincidence, the observations collected during the coming weeks will advance our understanding of how objects from both the outer solar system and interstellar space respond to the intense radiation environment of the inner heliosphere. The enigma behind the Sun may hold keys to understanding not only our own cosmic neighborhood, but also the nature of matter and energy flows in the galaxy beyond our heliosphere's protective boundary. Part 11. Solar Cycle 25 reaches a breaking point. The Sun is waking up, and it's doing so with a vengeance that has caught solar physicists off guard. Solar Cycle 25, which officially began in December 2019, has consistently exceeded predictions and continues to build toward what may become one of the most active solar maxima in decades. When the Solar Cycle 25 prediction panel issued their forecast in 2019, they projected a relatively weak cycle with a maximum sunspot number around 115, comparable to the previous cycle's disappointing performance. But the Sun had other plans. By 2023, it became clear that solar activity was significantly outpacing predictions, with sunspot counts, flare rates, and coronal mass ejection frequencies all running well above forecast levels. The September 28 M6-4 flare that erupted from active region 4232 fits perfectly into this pattern of enhanced activity. While M-class flares occur regularly during solar maximum conditions, the consistency and intensity of recent events suggest that Solar Cycle 25 may be building toward a crescendo that could rival some of the most memorable solar storms in recorded history. NOAA's Space Weather Prediction Center tracks solar activity through multiple indices that paint a comprehensive picture of our star's electromagnetic state. The F10.7 solar flux, a radio emission measurement that correlates strongly with overall solar activity, has shown sustained, elevated levels throughout 2024 and into 2025. X-ray flux measurements from the GO satellites reveal an uptick in background emission levels that indicates enhanced coronal heating across multiple active regions. Perhaps most significantly, the rate of Earth-directed coronal mass ejections has increased markedly over the past year. These billion-ton plasma bubbles, when toward our planet, can trigger geomagnetic storms that disrupt satellite communications, create spectacular aurora displays, and in extreme cases, threaten power grid stability through induced electrical currents. The physics underlying this enhanced activity involves complex interactions between the Sun's magnetic field and the plasma flows that transport energy from the nuclear furnace at its core to the visible surface. Active regions form where intense magnetic field lines emerge through the photosphere, creating the dark sunspots visible in white light images. These magnetic structures can build tension over days or weeks, as plasma flows twist and distort the field lines into increasingly unstable configurations. When magnetic tension exceeds the plasma pressure that normally contains it, explosive reconnection events release stored magnetic energy in the form of solar flares and coronal mass ejections. The energy scales involved are difficult to comprehend. A single large solar flare can release more energy than 10 billion hydrogen bombs, while the most powerful coronal mass ejections carry enough momentum to measurably affect planetary magnetospheres across billions of miles of space. Current solar activity patterns show several characteristics that distinguish this cycle from its recent predecessors. Active regions are persisting longer as they rotate across the visible solar disk, suggesting stronger magnetic field concentrations and more stable plasma confinement. The butterfly diagram, a plot showing how sunspot latitudes change throughout the solar cycle, indicates that the Sun may not yet have reached its maximum activity level, with peak conditions potentially still months away. Long-range magnetic connectivity across the solar surface has also increased with coronal holes and high-speed solar wind streams, creating free enhanced opportunities for magnetic field interactions between widely separated, active regions. This connectivity can lead to sympathetic flaring, where eruptions in one region trigger instabilities in magnetically connected areas thousands of miles away. The pre-Carrington analogies that some researchers draw require careful consideration. The 1859 Carrington event remains the most powerful geomagnetic storm in recorded history, causing aurora displays visible as far south as the Caribbean and telegraph systems catching fire across North America and Europe. Telegraph operators received electric shocks, and some telegraph lines continued operating even after their power sources were disconnected, drawing energy directly from the induced electrical currents. However, important differences exist between 1859 conditions and the current solar cycle. Our modern understanding of space weather allows for much better prediction and preparation than was possible in the 19th century. Satellite systems, while vulnerable to space weather effects, are designed with hardening and backup systems that didn't exist during the telegraph era. Power grid operators now receive real-time space weather forecasts and can take protective measures when extreme storms are predicted. What would constitute genuine evidence of a resonance saturation moment? A period when solar activity reaches levels that challenge current space weather infrastructure. The criteria include sustained sequences of X-class flares with associated fast-moving coronal mass ejections, multiple Earth-directed plasma clouds, arriving simultaneously to create compound geomagnetic storms, and F10. 7 flux levels approaching or exceeding the values recorded during previous solar cycle maxima. Current monitoring systems provide unprecedented visibility into solar activity patterns and their terrestrial effects. The GO satellite constellation continuously monitors X-ray particle emissions from the Sunday. The Solar Dynamics Observatory captures high-resolution images of active regions and their magnetic field evolution. Ground-based radio arrays track coronal mass ejection propagation through interplanetary space, while magnetometer networks around the world measure the effects of space weather on Earth's magnetic field. For the October 19th through 26th period, this monitoring infrastructure will be crucial for determining whether the convergence of SWAN 3I Atlas and enhanced solar activity produces anything beyond normal solar cycle variability. If electromagnetic coupling between comets and solar activity represents genuine physics, we should observe correlations in timing, intensity, or directionality that exceed random chance. The plain English risk assessment for this period includes the possibility of HF radio blackouts on the sunlit side of Earth if additional M or X-class flares occur. Such blackouts can disrupt aviation communications and amateur radio operations, but rarely cause lasting damage to electronic systems. Geomagnetic storms could produce aurora displays at unusually low latitudes if Earth-directed coronal mass ejections arrive during favorable magnetic field conditions. More severe outcomes remain possible if solar activity significantly exceeds current levels. Powerful geomagnetic storms can induce electrical currents in long conductors, like power transmission lines, potentially causing transformer damage or widespread blackouts in vulnerable grid systems. Satellite operations could be disrupted by enhanced radiation levels and atmospheric drag effects that alter orbital trajectories. As solar cycle 25 continues its climb toward maximum activity, the October convergence provides a natural experiment for testing whether cosmic coincidences can influence terrestrial space weather in measurable ways. Whether the answer proves to be yes or no, the data collected during this period will advance our understanding of how energy and information flow through the vast electromagnetic network that connects our Sun to every corner of the solar system. Part 12. Cometry, Resonance, and Planetary Stress. In the shadowy borderlands, where space weather meets seismology, a controversial hypothesis suggests that electromagnetic disturbances propagating from space to Earth might influence the timing of seismic events in ways that challenge conventional understanding of earthquake physics. The electroseismic storyline proposes that space weather-driven ionospheric perturbations could create cascading effects that nudge fault systems already approaching failure points, not causing earthquakes, but potentially affecting when they occur. This hypothesis requires careful examination because it touches on one of the most persistent and scientifically problematic claims in natural hazard research. For decades, earthquake prediction has remained one of science's most elusive goals. Despite enormous investments in monitoring technology and theoretical research, the fundamental challenge lies in the complexity of fault systems, where microscopic changes in stress, fluid pressure, or material properties can determine whether accumulated tectonic strain releases gradually through creep or suddenly through catastrophic rupture. The United States Geological Survey maintains an unequivocal position on space weather earthquake connections. No demonstrated causal relationship exists between electromagnetic disturbances and seismic activity. This stance reflects extensive statistical analysis of earthquake catalogues spanning multiple decades and solar cycles, consistently showing no significant correlations between geomagnetic storm intensity and seismic event timing or magnitude. Yet, alternative research communities continue to report intriguing correlations that suggest the relationship between space and Earth may be more complex than official positions. Acknowledged studies published in peer-reviewed journals have documented statistical associations between atmospheric and ionospheric anomalies and subsequent earthquake activity, particularly for large events in tectonically active regions. The proposed mechanisms fall under the broad category of lithosphere, atmosphere, ionosphere coupling, or LIIC, which suggests that electrical and electromagnetic processes might play previously unrecognized roles in seismic phenomena. According to these models, stress buildup in rock formations can generate electrical charge separations that propagate upward through the atmosphere to create detectable ionospheric disturbances, hours or days before major earthquakes occur. Laboratory experiments have demonstrated that stressed rocks can indeed generate electrical currents and electromagnetic emissions through piezo electric effects and other charge separation mechanisms. When extrapolated to the scale of major fault systems, these processes could theoretically produce electromagnetic signatures detectable by satellites monitoring ionospheric conditions. The controversial step in LIC models involves the reverse pathway, whether external electromagnetic influences might affect the electrical state of fault systems and potentially influence the timing of seismic events. Proponents argue that during periods of intense geomagnetic activity, such as those triggered by major solar storms, Ionospheric current systems could couple downward to affect the electrical environment of stressed crustal rocks. The energy scales involved present significant challenges for direct causation models. Even the most powerful geomagnetic storms induce electrical currents that are many orders of magnitude smaller than the mechanical forces involved in major earthquake ruptures. However, complex systems sometimes exhibit threshold effects, where small inputs can trigger large responses if applied at precisely the right moment and location. Historical analysis reveals intriguing patterns that deserve consideration despite the lack of established causal mechanisms. The 2011 Tohoku earthquake that devastated Japan occurred during a period of enhanced solar activity, though within normal variability ranges for solar cycle 24. The 2017 Chiapas earthquake in Mexico coincided almost exactly with extreme space weather conditions surrounding UMWAM's perihelion passage. The February 2023 Turkey-Syria earthquake sequence occurred during a period of elevated geomagnetic activity, though again within ranges that occur frequently throughout solar cycles. These examples highlight the central challenge in LIC research: distinguishing genuine physical relationships from the inevitable coincidences that occur when independent stochastic processes occasionally synchronize. Major earthquakes happen roughly once per week globally, while significant geomagnetic storms occur perhaps once per month during solar maximum periods. Random timing overlaps are statistically inevitable and cannot constitute evidence for causal relationships without much more sophisticated analysis. The testable approach to the October what-if scenario would involve Bayesian statistical analysis that compares global earthquake rates during periods of enhanced space weather to baseline rates during quiet conditions. Such analysis would need to account for normal temporal clustering in seismic activity, seasonal variations in earthquake detection, and the multiple comparison problems inherent in testing many possible correlations simultaneously. The methodology would involve defining specific criteria for enhanced space weather conditions, perhaps KP indices exceeding 6 for more than 24 hours, or X-class solar flares with associated Earth-directed coronal mass ejections. Global earthquake catalogues would then be analyzed to determine whether the rate of magnitude 7 or larger events increases significantly during such periods compared to baseline expectations. Communication ethics become crucial when discussing earthquake space weather correlations, because public safety depends on accurate risk assessment and appropriate preparedness measures. The temptation to narrate uncertainty in ways that create fear or false hope must be balanced against the scientific responsibility to acknowledge interesting correlations while maintaining clear distinctions between correlation and causation. The key message must emphasize preparedness culture over prediction claims. Earthquake preparedness remains essential in seismically active regions regardless of space weather conditions, because the overwhelming majority of major earthquakes occur during periods of completely normal solar activity. Any potential space weather influence on seismic timing would represent a minor modulation of earthquake probability rather than a reliable prediction tool. As the October convergence approaches with enhanced solar activity coinciding with SWAN's closest Earth approach and 3E Atlas near perihelion, the global seismic community will have an opportunity to test whether apparent correlations between cosmic events and terrestrial responses reflect genuine physical coupling, or merely the human tendency to find patterns in random data. The coming weeks may reveal whether electromagnetic connections between space and Earth extend beyond the well-established realm of communications and power grid disruption into the more controversial territory of seismic influence. Either outcome will advance our understanding of how energy and information propagate between the cosmic and terrestrial domains that define human experience on this small planet, orbiting through an electromagnetically active solar system. Part 13. Mars, 3I Atlas, and the shadow alignment. While Earth-based observers struggle to glimpse 3I Atlas through the Sun's overwhelming glare, Mars finds itself in the enviable position of having front-row seats to one of the most significant interstellar encounters in recorded astronomical history. The geometry unfolding in early October places the red planet in an optimal location to study this mysterious visitor. As it approaches perihelion and potentially develops the kind of spectacular coma that could reshape our understanding of past interstellar matter, the orbital mechanics paint a picture of remarkable precision. Around October 3rd, 3 Atlas will pass within approximately 30 million kilometers of Mars, roughly 0.19 astronomical units, or about 80 times the distance between Earth and our Moon. While this represents a substantial missed distance in human terms, it places Mars-based instruments within excellent range for detailed spectroscopic analysis, dust particle detection, and monitoring of any electromagnetic interactions between the interstellar visitor and the solar wind. This encounter carries profound significance because it may represent our best opportunity to study an interstellar object during its most active phase. Unlike Oumuamua, which remained largely inert during its passage through the inner solar system, and 2I Boris, which developed only a modest coma, 3I Atlas shows tantalizing signs of potentially more dramatic activity as it approaches maximum solar heating. The European Space Agency has recognized this opportunity and announced that multiple Mars-orbiting spacecraft will be tasked to observe 3 Atlas during its closest approach. Mars Express, which has been studying the red planet since 2003, carries instruments capable of high-resolution spectroscopy that could reveal the composition of any developing coma. The ExoMars Trace Gas Orbiter, designed to analyze atmospheric chemistry, possesses sensors that might detect exotic volatile species sublimating from the interstellar nucleus. Most intriguingly, these observations will occur just as Earth experiences its closest approach to SWAN, around October 20th through 21st. The near simultaneity of these encounters creates an unprecedented opportunity to study how objects from 2 very different reservoirs, the outer solar systems, Oort cloud and interstellar space, respond to similar levels of solar radiation and electromagnetic environment. The comparison promises to reveal fundamental differences in composition, structure, and behavior between solar system natives and interstellar wanderers. SWAN, formed from the same primordial materials that created our Sun and planets 4.6 billion years ago, should exhibit the characteristic volatile content and dust properties familiar from hundreds of previously studied comets. 3I Atlas, by contrast, carries the chemical signature of an entirely different stellar environment and potentially exotic materials that have never existed within our heliosphere. Theoretical possibilities emerge when considering how a large outgassing interstellar object might interact with the structured solar wind environment near Mars. The planet's thin atmosphere and weak magnetic field create a complex electromagnetic boundary, where solar wind particles interact directly with atmospheric constituents. If 3I Atlas develops a substantial coma rich in ionized gases, it could locally alter the plasma environment that Mars experiences during the encounter. Drawing parallels to comet sighting, Spring's 2014 encounter with Mars provides a framework for understanding potential effects. That Oort cloud visitor engulfed Mars in its extended coma and triggered the most intense meteor shower in Martian history, depositing metallic ions throughout the planet's upper atmosphere and creating ionospheric disturbances that persisted for days after closest approach. The energy deposition from Siding Spring was substantial enough to heat Mars's upper atmosphere by several hundred degrees, demonstrating that comets carry sufficient material and energy to measurably affect planetary systems. If 3I Atlas proves to be a more substantial object with greater outgassing potential, the effects on Mars could be even more dramatic. But 3 Atlas offers something that Siding Spring could not: insight into the electromagnetic properties of interstellar space itself. If the object carries embedded magnetic fields from its original stellar environment, or if its plasma interactions exhibit signatures that differ from solar system materials, Mars-based observations could provide the first direct measurements of how interstellar matter integrates with heliospheric conditions. The shadow alignment aspect of this encounter adds another layer of complexity to the October convergence. While 3E Atlas remains largely invisible from Earth due to its low solar elongation, its position places it in direct electromagnetic contact with the same heliospheric current sheet layers that SWAN is traversing. Both objects, despite their vastly different origins, find themselves embedded in the same complex electromagnetic environment, just as Solar Cycle 25 shows signs of building toward enhanced activity levels. Could the combined plasma output from two large active objects traveling through the same current sheet layer create measurable perturbations that propagate throughout the heliospheric circuit? This question ventures into highly speculative territory, but the physics of plasma loading and electromagnetic coupling suggests that such interactions, while likely subtle, might theoretically be detectable by sensitive instruments monitoring solar wind conditions. Parker Solar Probe, measurements of magnetic field structure, and particle populations near the Sun could provide crucial data for testing whether the October convergence produces any signatures of enhanced electromagnetic coupling between multiple solar system objects. The challenge lies in distinguishing genuine physical effects from the natural variability that characterizes all space plasma environments. For Mars-based observations, the focus will likely center on documenting 3 Atlas's composition, outgassing behavior, and any electromagnetic signatures that distinguish interstellar materials from their solar system counterparts. Spectroscopic analysis might reveal exotic, volatile species that don't exist in typical solar system comets, while particle detectors could measure dust properties that reflect entirely different formation environments. The timing of this encounter, occurring just days before SWAN's closest Earth approach and weeks before 3I Atlas reaches perihelion, creates a natural progression of observational opportunities. Mars provides the reconnaissance data that will inform Earth-based observers about what to expect, as both objects continue their journeys toward maximum solar heating and potential peak activity. Whether the October convergence reveals dramatic interstellar comet behavior or simply confirms that cosmic visitors, regardless of their origins, follow predictable physical laws when subjected to solar radiation, the observations collected by Mars-based instruments will expand human knowledge about the nature of matter and energy in our galactic neighborhood. The Red Planet, often viewed as a destination for future human exploration, may prove equally valuable as an observational platform for studying the cosmic visitors that occasionally grace our solar system with their presence. As 3 Atlas approaches its moment of maximum solar exposure, Mars stands ready to document whatever secrets this interstellar wanderer might reveal about the universe beyond our Sun's protective influence. Part 14. The Great October Window. The calendar pages turn toward the most precisely choreographed celestial convergence in recent astronomical history. 7 days that could redefine our understanding of how electromagnetic energy flows through the solar system, or confirm that even the most remarkable cosmic coincidences remain nothing more than the inevitable mathematics of orbital mechanics playing out across the vast stage of interplanetary space. October 19th marks the opening of our observation window, as SWAN continues its approach toward minimum Earth distance. By this date, the comet will have been traveling for nearly a month since its mysterious September 26th outburst, providing time for any shock waves or coronal mass ejections from the September 28th solar flare to traverse the 40 million miles of space separating the Sun from SWAN's orbital position. If electromagnetic coupling between the comet and solar activity represents genuine physics, this period should reveal the first evidence of interaction. Ground-based observers equipped with telescopes and cameras should watch for sudden changes in SWAN's tail morphology. The kinds of disconnection events, brightness surges, or structural reorganizations that have historically marked encounters between comets and solar wind disturbances. October 21st stands as the mathematical center of our convergence window. On this date, 3 separate astronomical events achieve simultaneous precision that occurs perhaps once in a human generation. The new moon eliminates lunar interference, creating the darkest possible skies for comet observation just as SWAN reaches its closest approach to Earth at 2,606 astronomical units, roughly 10 million miles. Meanwhile, 3I Atlas continues its stealthy approach toward October 30th perihelion, hidden behind the Sun's glare, but potentially developing the kind of massive coma that could locally alter solar wind conditions. The new moon timing deserves special attention because it represents the optimal observational geometry for detecting subtle changes in cometary behavior. Without scattered moonlight contaminating the sky, ground-based photographers and visual observers will have maximum sensitivity for recording tail structure, coma brightness variations, and any sudden morphological changes that might indicate electromagnetic interactions with solar wind disturbances. For space weather monitoring, the October window requires comprehensive surveillance of multiple data streams that could reveal evidence of comet-solar coupling. The geostationary operational environmental satellites will continuously monitor X-ray emissions from the Sun, watching for flare activity that correlates with comet positions or activities. Solar and heliospheric observatory coronagraphs will track coronal mass ejection, development and propagation, determining whether any plasma clouds appear to be directed toward regions of space where SWAN or 3I Atlas are located. Radio astronomy plays a crucial role in detecting the electromagnetic signatures of plasma interactions. Type 2 radio bursts indicate shockwave propagation through the solar wind, while Type 3 bursts suggest energetic electron acceleration associated with magnetic reconnection events. Coordinated observations from multiple radio telescopes could potentially detect coherent emissions associated with current flows between comet positions and solar active regions, the kind of signatures that would constitute direct evidence of electromagnetic coupling across millions of miles of space. Ground-based magnetometer networks provide another crucial monitoring capability during the October window. If comet-solar interactions can influence terrestrial space weather, enhanced geomagnetic activity should accompany periods of apparent electromagnetic coupling. The KP index, derived from magnetometer measurements around the world, offers a real-time gauge of how space weather conditions affect Earth's magnetic field. Probabilistic forecasting for this period must balance the excitement of potential discovery with the sober realities of space weather prediction. NOAA's Space Weather Prediction Center maintains appropriately cautious positions about solar activity forecasting, emphasizing that individual flare events remain essentially unpredictable more than a few days in advance. While statistical models can estimate the probability of flare activity based on active region characteristics and historical patterns, precise timing and intensity predictions lie beyond current capabilities. The fringe versus mainstream dichotomy that characterizes much discussion of comet-solar coupling requires careful navigation during the observation period. Mainstream space physics expects routine comet behavior, modulated by ordinary solar wind variations. Perhaps some tail disconnection events if SWAN encounters shock waves from recent solar activity, but nothing that would challenge established understanding of how electromagnetic energy flows through the solar system. The electromagnetic coupling hypothesis, while speculative, makes specific, testable predictions that extend beyond ordinary expectations. If comets embedded in the heliospheric current sheet can influence solar activity through plasma loading effects, the October convergence should produce timing correlations between comet activities and solar flares that exceed random chance. Radio telescopes might detect coherent emissions linking comet positions to solar active regions. Particle detectors could measure anomalous populations of energetic particles that trace back to cometary plasma sources. Safety considerations for the October window focus on the well-established effects of space weather on technological systems and human activities. High-frequency radio communications may experience blackouts during solar flares, affecting aviation operations and amateur radio communications. Enhanced geomagnetic activity could trigger aurora displays at lower latitudes than normal, while potentially disrupting satellite navigation systems and causing minor fluctuations in power grid operations. More severe outcomes remain possible if solar activity significantly exceeds current prediction levels. Powerful geomagnetic storms can induce electrical currents in long conductors like power transmission lines, potentially causing transformer damage in vulnerable grid systems. Satellite operations could face increased radiation hazards and atmospheric drag effects that alter orbital trajectories. The citizen science opportunity presented by the October window cannot be overstated. Amateur astronomers and photographers around the world will have optimal viewing conditions for documenting SWAN's behavior during its closest Earth approach. Standardized observational protocols, including precise timing, location data, equipment specifications, and photo trick measurements, could contribute valuable data for analyzing potential electromagnetic interactions between the comet and solar wind disturbances. Social media platforms and astronomy forums provide unprecedented opportunities for real-time data sharing and collaborative analysis. Images of SWAN captured from different geographic locations and time zones could reveal rapid changes in tail morphology that might otherwise go undetected by professional observatories with limited observing time allocations. As October 26th closes our observation window, the data collected during these 7 crucial days will either support or refute hypotheses about electromagnetic coupling between comets and solar activity. The answer may reshape our understanding of how energy and information flow through the solar system, or it may simply confirm that remarkable coincidences remain coincidental regardless of their precise timing. Either outcome represents a victory for scientific methodology and human curiosity about the cosmic forces that shape our corner of the universe. The October window offers a rare opportunity to test speculative ideas against observational reality, the kind of natural experiment that advances knowledge regardless of whether initial hypotheses prove correct or incorrect. Part 15. The Meta Pattern: Consciousness, Resonance, and the Living Cosmos. As our investigation draws toward its climax, we find ourselves confronting questions that extend far beyond the specific mechanics of comets, solar flares, and electromagnetic coupling. The October convergence, whether it proves to be choreographed or coincidental, illuminates something profound about the nature of pattern recognition, scientific inquiry, and humanity's relationship with the cosmos that surrounds and shapes our existence. From nova photons racing across interstellar space at light speed to cometary plasma clouds streaming away from ancient nuclei at 30 kilometers per second. From coronal mass ejections carrying billion-ton payloads of magnetized plasma to the subtle ionospheric currents that may couple space weather to planetary processes. We are witnessing manifestations of a single, interconnected plasma ocean that extends from stellar cores to planetary atmospheres across scales that challenge human comprehension. The system's perspective reveals patterns within patterns, feedbacks within feedbacks, and thresholds that connect seemingly independent processes across vast ranges of space and time. The challenge lies in distinguishing genuine physical relationships from the inevitable correlations that emerge when complex systems interact across multiple scales simultaneously. The credible mysteries revealed by interstellar visitors like 3 Atlas expand our prior assumptions about what kinds of objects populate the galaxy beyond our heliosphere's boundary. Each new interstellar visitor carries information about stellar formation processes, galactic chemical evolution, and the physical conditions that exist in the vast spaces between stars. These cosmic messengers test our theoretical models and occasionally reveal phenomena that require entirely new categories of explanation. 3 Atlas, with its potentially substantial coma and unusual composition, represents exactly this kind of paradigm-testing object. If it proves to contain hypervolatile materials or exotic dust properties that differ significantly from solar system analogies, astronomers may need to revise fundamental assumptions about comet formation and evolution in different stellar environments. The humility clause requires acknowledging that solar variability dominates electromagnetic processes throughout the heliosphere by margins that make cometary contributions appear negligible in most circumstances. The Sun contains 86% of the solar system's mass and generates magnetic fields strong enough to deflect galactic cosmic rays across billions of miles of space. Any electromagnetic coupling between comets and solar activity must operate within these overwhelming energy gradients. Yet complex systems science teaches us that dominance by large-scale processes doesn't preclude the existence of subtle feedback mechanisms that operate under specific conditions. In plasma physics, small-scale instabilities can sometimes cascade into large-scale reorganizations when threshold conditions are met. The key lies in identifying when and where such threshold effects might occur. If weak, transient electromagnetic coupling between comets and solar activity exists, it would likely appear as barely significant timing biases in large statistical samples. Exactly the kind of pattern that requires careful analysis to distinguish from random fluctuations. Individual events, like the September sequence, might remain ambiguous, but systematic analysis across many solar cycles could potentially reveal subtle correlations that point toward genuine physical processes. This possibility suggests an important role for citizen scientists and amateur observers in advancing understanding of solar system electromagnetic coupling. Professional observatories have limited time allocations and typically focus on well-defined research programs with established theoretical foundations. Speculative hypotheses about comet-solar interactions may receive minimal attention from mainstream research institutions, but amateur astronomers, equipped with increasingly sophisticated digital cameras and spectrometers, can contribute valuable data for testing electromagnetic coupling hypotheses. Coordinated observational campaigns, during periods like the October convergence, could generate datasets large enough to detect subtle statistical signatures that might otherwise remain hidden in the noise of normal solar system variability. The adventure of scientific discovery requires maintaining both wonder and skepticism, embracing the possibility that the universe may be more interconnected than current models suggest, while demanding rigorous evidence for any claims about new physical processes. This balance between openness and skepticism represents the essential tension that drives scientific progress. As October 21st approaches, we stand at one of those rare moments when theoretical speculation meets observational opportunity. The convergence of SWAN's closest Earth approach, 3I Atlas's hidden journey toward perihelion, and enhanced solar activity creates conditions that could either confirm or refute hypotheses about electromagnetic coupling across the solar system. The beauty of this situation lies not in predetermined outcomes, but in the process of scientific inquiry itself. Whether the October convergence reveals dramatic evidence of cosmic interconnection or simply confirms the power of coincidence to create compelling narratives, we will have advanced human understanding of the electromagnetic environment that shapes our existence as conscious beings embedded in a vast, dynamic, and occasionally surprising universe. The meta-pattern that emerges from our investigation suggests that consciousness itself may be the most remarkable phenomenon in this cosmic story. The ability to observe, analyze, and find meaning in the complex dynamics of plasma, magnetic fields, and gravitational interactions represents an extraordinary achievement in the universe's ongoing experiment with organized complexity. Whether we are witnessing choreography or coincidence during the October convergence, we are certainly witnessing the power of human curiosity to transform observations of distant astronomical events into opportunities for deeper understanding of the physical processes that connect our small planet to the vast Proinero. Electromagnetic networks that define our cosmic neighborhood. The final test of our ideas awaits in the data streams and photographic records that will emerge from the October observation window. But regardless of what those data reveal, the investigation itself demonstrates the profound human capacity to seek patterns, test hypotheses, and find meaning in the endless complexity of a universe that continues to surprise us with its beauty, violence, and occasional hints of deeper connections than we ever dared imagine.